All right, so a negative function for potential energy. How will that change the way we work with energy in our problems? Well, first of all, it doesn't change the fact that as an object moves from a high point to a low point, it loses potential energy. It's just that the mathematics looks a little bit different. Here's a graph that shows a potential energy function. Okay, it's a negative function, meaning that it's all below the x-axis, and it's an inverse function, which means that we have this shape to the curve. If an object moves from a high point to a low point, like here it's at r equals 12, here it's at r equals 4, the potential energy does decrease. Okay, it goes from this value, this level, down to this level. It's just that it's going from a negative value to a negative value. So negative 0.1 to negative 0.25. If I calculate the change in potential energy as this occurs, I should still take the final value minus the initial. So my final negative 0.25 minus my initial negative 0.1, this comes out to be a negative 0.15. I lose potential energy, or this object loses potential energy as it falls. If we were to somehow switch this around and call the ground zero, everything would get messed up, and we'd be talking about increasing potential energy as the object falls. And that way of thinking, it's going to be easier to change the math than it's going to be to change that idea of whether something gains or loses the potential energy. In terms of calculations and so forth, the total energy that something will have will still be a combination of potential and kinetic energies. Assuming no springs or anything like that are acting on an object, you're going to have potential energy, negative gmm over r, and you're going to have kinetic energy if the object is moving. If the object is not moving, it doesn't have kinetic energy. But this is the key thing. It's still going to have potential energy. At every point in a real object's motion, there is going to be potential energy, because the potential energy is only zero if the object is an infinite distance away. And realistically, that just doesn't happen. All right, so that's really a very key idea here when you're setting up problems, is that the total energy is going to be a combination of potential and kinetic. And the only way you're going to have one of these missing is if it's not moving and there's no kinetic, but there will still be potential energy. Let's take a look at an example here. This is going to be the first question on the homework set here. So imagine that we have a rocket being launched from the surface, which, we've done problems like this before. And we want to know, in this case, what is the speed when it reaches a certain point above the surface? How fast is it traveling? So we're talking about a situation something like this, but we're further away from the Earth's surface than we're used to working. This still is way exaggerated, this picture here, but we are moving from a position R1 to R2. But where's the potential energy zero? It's way over here, it's off the screen. It's an infinite distance away. So at both of these positions, the rocket will have potential energy. In fact, at both positions, it will have kinetic energy, because it's leaving the Earth with a speed of 1200, and we're trying to find its speed at this other position. So when we set this question up, we will include both types of energy at the surface and at this other position above the surface. All right, so let's be careful about this. Again, make sure you keep that negative sign in there for potential energy. It's very easy to slip and somehow cancel that out or something. But what we can cancel out is the masses. Okay, so similar to other problems we've done with potential and kinetic, the mass of the object does not matter. It drops out from the setup. Okay. All right, before we actually plug in some numbers, I want to point out something that might be useful to you as you work through some questions. You know, we use the mass of the Earth quite a bit in our problems, and this quantity, capital G times the mass, comes up quite a bit. So if you know you're working with the Earth, something you might want to do is to have this value of capital GM sort of set up already. It ends up being about 4 times 10 to the 14th. And that way you could just keep that GM chunked together. In fact, this is something that could be stored into your calculator as a value. We'll talk about that in class, how to do that, in case you're getting tired of plugging in all these huge numbers. All right, well, let's use this and plug into our formula here. So here's our G times M. Again, we got our negative sign still out here. And we're starting on the Earth's surface. And so the value of R is going to be measured from the center of Earth. And that is going to just be then the radius of the Earth since we're on the surface. We know the initial speed. Then after is when we reach that second point, R2, up in the air. So again, that same value of GM, got our negative sign. But now we're at an extra 10,000 meters above the Earth. So it's the radius of the Earth plus that 10,000 meter altitude. And then we're going to have what's left over from our kinetic energy formula after we canceled out M. All right, I'm going to show just a little bit of algebra here because these can get a little tricky. You may want to write an in-between step where you sort of combine together each term. Some people like to do that. Although if you're pretty good with your calculator, don't feel like you need to include this step. If you are able to work through the algebra consistently, that's perfectly fine with me. All right, but we do end up with a speed pretty high of about 1,100 meters per second, but it certainly is slower than the initial speed. And of course, that's what we would expect the rocket to slow down as it moves away from the Earth. All right, the last thing is I do want to talk about escape speed, kind of a cool idea. That's going to be just the final video, so you can move over to that if you are interested and kind of looking ahead. But this should give you a pretty good sense of how to do some initial questions using the conservation of energy. In the last video, we determined the speed that this rocket would have if it reached a certain height above the surface. But we can kind of add a little bit more to that, answer a second question, where we wonder how high can the object actually go? Okay, it was still traveling at 1,100 meters per second when it was 10,000 meters above the surface. How high will it actually reach before it starts to fall back down towards the Earth? Right. So this is question 2 then on your practice work. How high will the rocket reach when it runs out of speed? All right. So in this case, when we compare the energies at 2 different locations, we'll look at the energy at the surface and then the energy at the highest point. But just like when I throw a ball up into the air close to the Earth, and it only has potential energy at that top point spot because the kinetic energy is 0, that's the same thing here. There is potential energy, but there is no kinetic energy. The only real difference here is that even when the rocket was at the surface of the Earth, when it was first launched, it still has potential energy. That's the change from just launching a rocket like a toy rocket and having it go up into the air. All right, so our M's can cancel. Again, the mass of the rocket really doesn't matter. And we can put that GM chunk again in there. That's where the 4 times 10 to the 14th comes in. And put some values in. And so what we're going to initially try to find is at what value of R does it run out of speed. Although that won't be our final answer because that's from the center of Earth to this location. And the question asks how high above the Earth. So we will have to do a little bit of work after this initial calculation here. All right, when we work our way through this, we may want to calculate what that what this side of the equation ends up being. Notice that this would it wouldn't exactly equal the total energy because we canceled out the mass, but it still, even if we had the m in there, it still would be a negative value. That's kind of an interesting point that we'll talk about more, is that the total energy with this new version of potential energy, the total energy is negative. All right, so as we work our way through this, we find that R is 6.47 times 10 to the sixth. It's actually not that much bigger than the radius of the Earth. Let's go ahead and find now the actual height above the surface of the Earth. So to find that height, we would take this value of R and we would subtract the radius of the Earth, so that we would only get this distance from R, like our R1 to our R2. So when we subtract the radius of the Earth, 6.4 times 10 to the sixth, we get about 70,000 meters. All right, so it only went, or we were looking earlier at a point of 10,000 meters above the Earth.